All right, today is where we pass the sign that says, "Abandon all hope, ye who enter here." Nah, it's not that bad. It looks bad, but it's not that bad. So welcome to something called Titration Curves. And in previous years, honors chemistry and stuff, and I would ask you to do a titration, and all you were trying to really do was find the concentration of the unknown. What's the concentration of acid? What's the concentration of base? And we didn't really go any deeper than that. Today, we're going to be asking what goes on in a titration. What's really happening? Towards the end of this procedure, you're going to be able to construct what's called a titration curve. What a titration curve does is it tells us for every volume of the titrant, that's the known, that we add to our unknown, what happens to the pH? Well, if you're titrating acid, which has a pH of less than 7 with base, what you'll find is that as you add your titrant and the base begins to slowly neutralize the acid, the pH starts to rise. Well, eventually you reach this point called equivalence. A lot of times they just abbreviated EQU, where there's no more acid left to be neutralized. In the normal titrations that we've done, this is where we reach what's called trigger or equivalence, or where the indicator starts to tell us that there is no more acid and starts to change color. In a pH curve, a titration curve, what ends up happening is now there's no more acid left. Now the pH begins to jump all the way to the side of being basic, and that's what a titration curve looks like. And I want to show you how we do this. And here's an example of a problem. Now this is on OneNote. I usually assign this one, but I'm going to use this one as an example this year. Let me put this up here. This says, consider the titration of 100 milliliters of a 0.2 molar acetic acid solution. It gives us a Ka with 0.1 molar potassium hydroxide. And it says calculate the pH of the resulting solution after we added these 6 different volumes. Well, 5, because part A is just 0. So let's do part A. Let's get that out of the way. And you guys know how to do this. You could use your old school calculations for calculating pH, and we know that Ka for acetic acid, it tells us it's got Ka of 1.8 times 10 to the negative fifth, and you could set up the whole equation. By now you know that we're solving for X, and X is going to be H+. It's also the acetate, and underneath is our initial concentration. It's 0.2 molar, and you know that when you crank all this out, X, which is equal to H+, let's do it. 1.8 times 10 to the negative fifth times 0.2. We're going to take the square root of that, and we get 0.0019 molar. And if we plug this in for pH, we're simply taking the negative log over H+, and we get 2.72. That puts us right here on our curve, okay? Let's highlight this. Whoops, that's supposed to be the highlighter. All right, now let's go on to part B. Part B is asking us what happens when we titrate with 50 milliliters of 0.1 molar potassium hydroxide. So I'm going to introduce you to a new term here because these numbers are pretty small. So I want to introduce you to something called millimole. Of course, a millimole, 1 millimole, is 0.001 mole. It's a useful number because we don't have to write all these decimals. And so if molarity is equal to moles over liters, it's also equal to millimoles over milliliters. And what's nice about this is that if we flip this equation around, moles is equal to molarity times liters And that means that millimoles is equal to molarity times milliliters. So here's why we're doing this. If we have 100 mils of 0.2 molar acetic acid, how many millimoles is that? So we have 100 milliliters of 0.2 molar. 100 milliliters of 0.2 molar acetic acid, HC2H3O2. Well, according to this, molarity, millimoles is equal to molarity times milliliters, and this is equal to 0.2 molar times 100 milliliters equals 20 millimoles. Why are we doing this? Well, in part B, we're neutralizing with 50 mils of 0.1 molar potassium hydroxide. So, 50 milliliters of 0.1 molar potassium hydroxide. That means that millimoles is equal to molarity, 0.1 molar, times milliliters. 50 milliliters equals 5 millimoles. Why are we bothering? Well, we're going to do what's called a before reaction and after reaction. When we're neutralizing HC2H3O2 with potassium hydroxide, we don't care about the potassium. We know it's going to dissociate completely. Well, this hydroxide is going to neutralize our acid. It will take this H off of our acid, and it will make H2O and leave the conjugate base. So it takes 1 mole of hydroxide to neutralize 1 mole of our acid, right? I mean, that's what acids and bases do. It doesn't matter that this is a weak acid. What this means is that this hydroxide is going to neutralize whatever H plus this is willing to give off. Well, we're starting with 20 millimoles of acetic acid, and we're starting with 5 millimoles of hydroxide. So we're going to call this before. What goes on before the reaction? We've got 20 millimoles of acetic acid, 5 millimoles of hydroxide, and before the reaction, nothing's happened. So we don't have any water, we don't have any acetate. After the reaction, these 5 millimoles have neutralized 5 millimoles of our acetic acid and leave 15 millimoles. There's no more hydroxide because they've all gone into making the water, and because there were 5 millimoles of hydroxide, they've made 5 millimoles of water and 5 millimoles of acetate. So, what is our new concentration? In fact, what we can do is we'll use our new friend, the Henderson-Hasselbalch equation. pH is going to equal pKa plus the log of the concentration of base over the concentration of acid. Well, what's our concentration of acid? After the reaction, we've got 15 millimoles of acetic acid that remain in solution, and we've got 5 millimoles of acetate that we just made. So let's get these into a concentration so we can plug these into our Henderson-Hasselbalch equation. So we're going to get our concentration by dividing by the final volume. Let's remember that this was 100 mils of acetic acid and 50 mils of potassium hydroxide. So everything's in 150 milliliters. So molarity is going to be equal to millimoles over milliliters. For our acid, this is 15 millimoles over 150 milliliters. And you shouldn't really need a calculator for that one. We get 0.1 molar. And for our base, we have molarity equals millimoles over milliliters. We've got 5 millimoles over 150 milliliters. And you might need a calculator for that one. I get 0.033 molar. What's the pH? Well, isn't it handy that we learned our Henderson-Hasselbalch equation last night? pH is equal to pKa plus log of the concentration of base over the concentration of acid. And since this is acetic acid, it's got a Ka of 1.8 times 10 to the negative fifth. That's a pKa of 4.74 plus the log of our concentration of base over the concentration of acid. Now let's remember that when we did this in step A, we got a pH of 2.72. We expect our pH to increase. What did we get? 4.74 plus log of 0.033 divided by 0.1, and I get 4.26. And that is right on this curve, right where we expect it. It was 2.72 here at 0. Now that we've added 50 milliliters of our base, now we're at 4.26. Let's try this next one, where we are adding 100 milliliters of base. So this is going to be C. 100 milliliters of 0.1 molar potassium hydroxide to 100 milliliters of 0.2 molar acetic acid. All right, so let's get everything into millimoles. We know that we have 20 millimoles of acetic acid. I don't know why I keep writing that little 2 there. And we have 100 milliliters times 0.1 molar potassium hydroxide is 10. Yeah, I want to make sure it's on the right spot. 10 millimoles of potassium hydroxide, which we know is going to dissociate into 10 millimoles of hydroxide. So let's do our before and after. Our reaction, HC2H3O2 plus hydroxide yields H2O and acetate. Well, we have 20 millimoles. This is the before reaction, 20 millimoles of acetic acid. This time we're adding 10 millimoles of base. Before the reaction starts, we haven't made any of that stuff. After the reaction, this 10 millimoles is going to neutralize 10 and leave 10. This will be 0. We'll have made 10 millimoles, and we'll have made 10 millimoles of our acetate. So I'm going to get these into concentrations, milliliters. Molarity is equal to millimoles over milliliters. We've got 10 millimoles of acetate. This is now, since we've added 100 mils of our base to 100 mils of our acid, our new volume is 200 milliliters. And it's always good to have a calculator just to be sure. This is 0.05 molar acetic acid, and let's do the same for our base. We did 10 millimoles of acetate after the reaction in our 200 millimoles. Look at that. These guys are now equal. I think you know what's going to happen when we plug this into Henderson-Hasselbalch. But let's do it anyway. And so pH is going to equal pKa plus log of base over acid. And these guys are both equal at this stage, 0.05 and 0.05. And so since the pKa is 4.74, and now we are doing the log of what is effectively 1, that means that at stage C, our pH is 4.74. Let's use our highlighter. I'm trying to get this to select the highlighter. Okay, so here on our curve, we're at now 4.74 at 100. All right, here is step D, 150 milliliters of base. All right, scrolling down all the way to the end. My computer's pretty slow today. Okay. Here, at step D, we are adding 150 milliliters of 0.1 molar potassium hydroxide to 100 milliliters of 0.2 molar acetic acid. All right, I think you guys are getting the hang of this. So I'm going to streamline things a bit. Here is our reaction. And this time we know that our acid before the reaction is 20 millimoles, so there's no need to calculate it. For our base, we have 150 mils of 0.1 molar, and so that's 15 millimoles. And before the reaction, those are both 0. After the reaction, this 15 will have neutralized 15 millimoles of our acid and left 5. This will be 0. We will have made 15 millimoles of water, and we'll have also made 15 millimoles of acetate. What are our concentrations now? So molarity equals millimoles over milliliters. For acid, it's 5 millimoles over what is now 250 milliliters total. And so our concentration is 5 divided by 250. This is 0.02 molar acetic acid. And let's do the same thing for our base. If molarity is equal to millimoles over milliliters, now we have 15 millimoles of acetate over our 250. Isn't this interesting that now the concentration of base is slightly higher than that of acid? Well, let's just see what happens. 15 divided by 250, and this is 0.06 molar. So let's see what we get when we plug that into our Henderson-Hasselbalch. pKa plus log of concentration of base over acid. And I'll be honest with you, I'm not entirely sure what's going to happen now. So we're going to say pKa. We know that for acetic acid it's 4.74 plus the log. Concentration of acetate, this stuff, is 0.06 molar, and concentration of acid is 0.02 molar. 4.74 plus log of 0.06 divided by 0.02 is 5.217. So right here at the very edge of our curve, we have a pH of 5.217, and that's at 150 milliliters of base. All right. Here at E, you can probably see what's going on. At E, we're adding 200 milliliters of 0.1 molar potassium hydroxide to, I'm just checking the time here, to 100 milliliters of 0.2 molar acetic acid. Okay, so here is our reaction. H, I keep writing that 2 there, and I don't need to do that. My erase function has stopped working, so HC2H3O2 plus OH minus yields water and acetate. Before the reaction, we had 20 millimoles of acetate, and how many millimoles of base do we have? Millimoles is equal to molarity times milliliters, so 200 times 0.1 is, look at that, ladies and gentlemen, 20 millimoles of hydroxide. They're exactly equal. Before the reaction, there's no water or acetate. After the reaction, this 20 millimoles neutralizes all of the acetic acid. That means there's no acetic acid and there's no OH minus. There is 20 millimoles of water, and there is also 20 millimoles of our acetate ion. Well, that acts like a base, ladies and gentlemen, and this is where the pH does this absolutely skyrocketing jump from pHs below 7 to pHs above 7. I'm waiting for OneNote to catch up, so I'm going to pause until it does. Now, this is this massive spike because there's no more acid left. There's just base. And that's why it takes place in this, vertical line. Let's go back down here and let's calculate what our pH is going to be here at stage E, where all that we have left is our 20 millimoles of acetate. First off, let's get the molarity. It's equal to millimoles over milliliters. This is 20 millimoles of acetate in what is now 200 and 100 is 300 milliliters, and this is 0.067 molar. So here's the difference. This C2H3O2 is a base. Kb is equal to Kw over Ka. If Kw is 1 times 10 to the minus 14th, Ka is the Ka of acetate, 1.8 times 10 to the negative 5th, then our Kb is 5.56 times 10 to the minus 10th. What is our pH at that concentration? You guys know how to do this, right? This is how we calculate the concentration of base into pH, where X is going to be this OH minus. If you do calculate X through the miracle of technology, I will find it instantaneously. You get a concentration of OH minus that is 6.1 times 10 to the minus 6th, which is a pOH of 5.21, which is 8.79. Okay, last step. So what happens in this last step? We've got one more step here, this guy, where we add 250 milliliters of our base So that's step F. Let's go there. We know the pH has been climbing, right? We've got all these going up in increments. You know, we started at, what did we start at? 2.72, and then we went up to 4.74, which is, I'm sorry, 4.26, and then we went up to 4.74, and then 5.217, and now at this point of equivalence, 8.79. Now we're at step F, where we're adding 250 milliliters of our 0.1 molar potassium hydroxide to our 200 milliliters of 100 milliliters of 0.2 molar acetic acid. All right, so we've been doing this for a while. We know that we have 20 millimoles of acetic acid. How many millimoles of the base do we have? Millimoles equals molarity times milliliters. It's 0.1 molar, and we have 250 milliliters. That's 25 millimoles of our potassium hydroxide. So if we know that the neutralization equation looks like this, what's going to happen when we add to our 20 millimoles of acetic acid 25 millimoles of base? Well, that's the before reaction. We know that when the reaction takes place, these guys are going to neutralize these guys. Well, there's only 20 millimoles to neutralize, so all those are gone. But there are still 5 millimoles of OH left over. We've made 20 millimoles of water. We've made 20 millimoles of acetate, but this guy is a wimp compared to this guy. I mean, that's a big cannon. So all we need to do is say, well, look, we made 5 millimoles of pure OH minus. None of this KB stuff required. It was 250 milliliters plus 100 milliliters. So what's our concentration of OH minus? We got 5 millimoles of OH minus in what is now 350 milliliters total solution. So taking out your calculator, 5 divided by 350 is 0.014 molar, and it's pure hydroxide, nothing to get in the way. So I'm going to calculate our pH, and I'm going to do that by getting POH. It's equal to negative log of the OH minus. In this case, it's 0.014 molar. So negative log of that answer is 1.84. That's our POH. Our pH is equal to 14 minus POH, and we get 14 minus our pH is 12.155. You see what's going on here? That's why titration is so frustrating, because once you get past the point of equivalence, the amount of hydroxide takes over, and that's why this thing shoots for the moon once you get right past that. So if you remember how frustrating titration was in honors chemistry, well, now you know why. All right, so this titration curve has 6 steps. I'm going to ask you to try one tonight that has a few more, and I'll give you the opportunity to talk to me about whatever you want, and also post the answer key. All right, you know the basic steps, nothing changes. All right, doesn't matter if there's 6 or 15. All right, take this for a spin. I'll see you guys on the next one.